Hello, my name is Seokhyun Hwang and I am currently pursuing my master's degree at Gwangju Institute of Science and Technology in South Korea. It is an immense pleasure and honor to be here today to share my research with all of you. I'll be presenting my paper titled Electrical Vibrational and Cooling Stimuli-Based Redirected Walking. Below you will find the names of my esteemed colleagues and professors who have collaborated with me on this research, and I'm honored to represent them and present our work with you. Without further ado, let us begin the presentation. Walking is crucial for immersive VR experiences, but real environments are often more limited than virtual ones. Redirected walking technologies resolve this by altering the user's path in the real space, creating a mismatch between real and virtual movements. Redirected walking allows seamless walking in virtual environment by dynamically changing the path to avoid obstacles through visual manipulations. In the video demonstration, the left shows the user with RDW and the right shows the user without RDW. Both are enjoying the same game, but the redirected walking users can traverse a larger area. RDW rotates the virtual map, enabling users to avoid obstacles, providing more immersive VR experiences despite physical limitations. However, redirected walking faces limitation when the user needed broader angle changes to avoid obstacles. Increasing visual manipulations can lead to visual-vestibular inconsistency, where users may notice the manipulation, reducing immersion and increasing simulation sickness. This limitation, known as detection threshold, restricts the user's path manipulation and expandable spaces. So we investigated using vestibular stimulation to reduce visual-vestibular inconsistency and expand the DT. Previous studies employed noisy galvanic current or directional galvanic current to expand DT, which can be used independently of content. Galvanic currents were evaluated as a promising technology to expand DT. However, GBS has safety concerns for pregnant women or pacemaker wearers and even regular users. Also, its usage is limited to 30 minutes per day. Our research aims to find alternative methods to mitigate visual-vestibular inconsistency and expand DT. This will help overcome RDW limitations and provide a more seamless and immersive VR experiences. Our study proposed a system that expands DT using non-electrical stimulations like bone-conduction vibration (BCV) and caloric vestibular stimulation (CVS), which can apply vestibular stimulation to users without using electrical stimulations. We compared this with electrical stimulations like noisy and directional GBS. So we measured DT and evaluated usability in a simple RDW game environment to study user experiences. This study aims to make RDW technology more accessible and safer for users experiencing side effects from electrical stimulation, and ultimately enhancing the immersive experiences in virtual reality. Next, we will describe the device we have developed for our study. We have created a total of 3 devices: GBS, BCB, and CBS. We kindly ask you to refer to our paper for detailed specifications and manufacturing method due to time constraints. First, I will explain the GBS devices. The GBS device has been designed to support 2 different stimulation methods. Directional GBS involves applying a current to 4 electrode positions as shown in the figure. There are 3 different stimulation methods depending on the polarity and the applied positions. Through previous studies, it has been confirmed that each stimulation method can apply vestibular stimulation in a lower pitch and yaw direction. Next, we have the second GBS stimulation method, noisy GBS, which uses white Gaussian noise current stimulation similar to previous studies of Matsumoto et al. For safety reasons, we have limited the stimulation to 15 volt and 2 mA. Below is an image of our devices we have created. Next is the BCB device used in our study. BCB induces displacement of fluid in the vestibular limbasis through vibration, creating vestibular noises. According to a previous study, BCB of 200 Hz to 500 Hz generates the largest vestibular stimulation, and this study used vibration of 500 Hz. And next is the CBS device used in our study. CBS regulates fluid density of the vestibular organ by stimulating the external auditory corner with the cold air. So we use Peltier module to create cooled air, which you can see in the image in the bottom right. Okay, and next we will introduce the two experiments conducted in our study. The first environment investigates quantitative factors such as DT expansion performance, simulator thickness, gait stability, and stimulus discomfort. And in the second environment, each vestibular stimulus was applied to a simple game environment to investigate user experience in an actual game scenario. So we investigate immersion and presence task performance and simulator thickness and discomfort in a simple ball finding game environment. Yeah, we have some footage from our experiments. The first scene shows the participants' game view in the experiment 1 condition. And the following scene features a participant during experiment 2, and every details will be provided in the upcoming section. The first experiment was conducted in an environment which was designed based on DT measurement environment from previous research. Participants were asked to detect the application of randomly applied gains, and through this, we measured the range of gains that user could detect. For more detailed information on our experiment design, please refer to the published paper. The result of experiment shows the following DT expansion performance for each vestibular stimulation. Directional GBS recorded the highest DT expansion, followed by BCB, CBS, and noisy GBS, which expand the DT as shown in the table. Through this result, we were able to prove that non-electrical vestibular stimulation can effectively expand the DT. Furthermore, the gait stability of each vestibular stimulation RDW system is as follows. The graph represents more unstable walking as the values increases. We confirmed that adding noise to vestibular stimulation increasing working instability, so the noisy GBS, BCB, and CBS has limitation in making walking slightly unstable. Next is the simulator thickness and discomfort of the participants who receive each stimulation, but due to time constraints, I will discuss the analysis of this aspect later in the summary section. Next, we investigate the user experiences when vestibular stimulation is applied in the game environment using a simple ball finding game with an RDW as seen in the video earlier. Participants were asked to find as many ping balls as possible within a limited time while redirected walking was applied. The experimental results show that there was no significant differences in presence for all conditions. Therefore, we conclude that all vestibular stimulation do not impair immersion in the game. Next, we compared task performance to investigate whether the vestibular stimulation interfere with the game's task. The results show that except for CBS, all vestibular stimulation did not interfere with the game's task. However, CBS significantly hindered achieving the objective of the game. Next is the simulator sickness and discomfort of the participants, but due to time constraints, I will discuss the analysis of these two aspects later in the summary section. In summary, experimental 1 showed that the BCB and CBS extend the curvature DT and directional-based stimulation provide a more stable gait. Experimental 2 revealed that non-electrical stimulation caused high discomfort and motion sickness but didn't impact task performance or immersion in the game. Directional GBS, however, caused motion sickness and discomfort, especially in the game environment. And in conclusion, our study provides valuable insight to the potential of various vestibular stimulation methods for enhancing the detection threshold in the redirected walking, and ultimately contributing to the development of more immersive virtual reality experiences. For a more detailed analysis and discussion, we encourage you to refer to our published paper.